Dodie, would you believe it? Today is episode number 50.
50. Wow.
I know. Does it make you feel old?
Oh, I'm already older than 50, so let's not talk anymore about that.
Well, you know, we have come a long way, and I just thought, let's think about how far we've come in the last 50 years. So let's talk about space.
Are we going to talk about poop in space?
Maybe we could get there. I mean, you know, poop and bugs and fungus, you know, all the things that I love the most.
It's inevitable on this podcast.
Mm-hmm. So we're going to infinity and beyond, and I'm going to make as many sci-fi puns as I can because, Dodie,
That's what matters.
That's what matters on Discovery Matters.
The water industry on Earth is rather conservative, right?
So this is Jörg.
So my name is Jörg Vogel. I'm the VP of Open Innovation at Aquaporin and have worked on our space-related ventures since the beginning in 2011, I think was the first contact.
Aquaporin, where have I heard that before?
The Royal Swedish Academy of Sciences has today decided to award the Nobel Prize in Chemistry for 2003 for discoveries concerning channels in cell membranes, with one half of the prize to Peter Agre, Johns Hopkins University School of Medicine, Baltimore, USA, for the discovery of water channels, and one half of the prize to Roderick McKinney.
You may remember that back in 2003, Peter Agre was awarded the Nobel Prize in Chemistry for discovering aquaporin water channels in 1992.
Okay, so what exactly are aquaporins?
Well, Jörg told me that basically in a nutshell, an aquaporin is the water channel made by proteins that spans the cell membrane and transports water, and only water, in and out of cells.
So it's like essentially regulating the water content of a cell. And it's a passive channel, so it's actually not transporting actively. It relies on osmotic pressure differences. So it is just the part of the cell membrane that like decides what water goes in, like clean water mainly, because it is a pure H2O transporter. Nothing else can pass the channel. So it's a very selective tool. And that's what nature does best.
So it's a hole in the cell membrane through which, how does nothing other than water pass through that?
It's genius, isn't it? Life is so amazing. So 1 gram of aquaporins, these tiny little holes, can filter up to 700 litres of water per second. So the practical use here on Earth, where around 71% of our surface is covered by water, but less than 1% of that is safe to drink. Well, there you go. It's exciting, to say the least.
We have everything from household water purifiers that can be used in households to filter tap water where you can't drink it directly to make it safe to drink, or you just want to have some kind of water that tastes a bit different because it's a bit demineralized, so it's softer. You all the way to kind of like high pressure applications where we go into industrial wastewaters to like clean industrial waters or generate drinking water from surface water, for example.
Okay, love that. But I thought you promised space.
Okay, yes, we are. And now maybe time to beam us up, because in 2011, Jörg and his colleagues at Aquaporin headquarters were contacted by none other than NASA.
They are a constant lookout for new technologies. They don't like shy away from a bit of a like risking it to like try something new, because whatever can help them to make it more efficient, everything helps, right? If you look at like long-term travel or long space flights, Mars travel and so on, like the less water you have to ship up and with them, the better it is, because it's quite expensive to set that stuff up.
So there, Jörg is suddenly in one of NASA's research centers, bang in the heart of Silicon Valley.
The first tests we did with our very first prototypes were actually in the NASA Ames labs in California. We've never tested it outside of our own lab. The first time we tested it was there.
Okay, so what excited NASA so much about aquaporin inside membrane technology? I mean, what could they do with aquaporin in future space exploration?
Well, think about just living in a closed environment like the International Space Station. I mean, where does the water come from and where does it go?
Basically, their water sources they have up there is water they ship up or like they fly up, and then urine and condensate. So basically, like all the water you breathe out, like the humidity and so on, is like recovered and like and so on. And there are certain contaminants in there. And of course, urine is the biggest source of water they have because it's the water they use every day. And then they mix that, what comes out of that treatment with the condensate and then run it through different processes, which is like a big cupboard that's built up there at ISS. It works. It's stable. So that's fine. They're not looking necessarily to replace them.
But for Jörg, the ISS is just small potatoes. When it comes to the future, he's thinking big.
When you talk about kind of the lunar orbiter or like this gateway they want to build, that's going to be a space station that's not necessarily inhabited the whole time. And it's going to be more space constricted. So like you have to like get some new kind of solutions in there.
And that's where Jörg and aquaporin come in.
We want to make like a compact unit to treat the urine and condensate directly and without further treatment steps. So like take that concept, like take as much water out as we can, and then make, in the end, it comes drinking water out. So your input is urine and condensate, output is potable water. And it should be like a very like compact size unit that has some certain requirements in energy use and so on and so forth, can be shut down and started up again without bigger complication, because that's also like quite a challenge, this kind of like pausing of processes, which makes it even more difficult.
Whoa, okay. So how is it actually tested? Is there somewhere on Earth where they can test it in like a space-like tunnel?
You could test it on Earth if you wanted to, if you weren't amazing and didn't have access to the International Space Station itself, which is what they did. In September 2015, the Danish astronaut Andreas Mogensen performed a space test of the aquaporin inside membranes on the space station itself.
When he had his tour up into space, so he tested it in a proof of principle test. Nothing that he could drink or anything, but like just a proof of principle. So we know it works, the membrane filtration in space, and now we have to kind of build a unit where we take into account all kind of challenges we could encounter, build a flight unit, and then basically wait until we get the time and money and funding to like go up to ISS and test it.
And what's really fascinating for me is the fact that all of this concept is what we call biomimetic.
Okay, so now you're going to tell me how this connects to life sciences, I hope.
Yes, of course. So biomimicry or biomimetics is where ideas for engineering solutions and chemistry come from biology, right? So we look at how life has solved problems over a period of millions of years using evolution, and we think about applying that to problems that we're facing in materials or machines and functions that, we need our technologies to perform.
Why invent new things if it's already the best solution is out there? We just need to harvest it somehow.
So we watch science fiction, and some of them are really sort of hyper-realistic, based on real physics and so on, but they never address those issues about, like, where does all the wee go, and how do they shower, and where's the water coming from? And so I just loved geeking out with someone about filtration and membrane technologies in space. So, this was like all of my dream interview questions come true, but never fear, I'm not finished yet. There's more geeking out. Say you've bought some real estate on Mars.
As one does. Oceanfront property.
Why not? Trading in futures.
Mars is absolutely a limited resource environment.
Oh, this is a new voice. Who's this?
This is Chris.
Chris Maurer. I'm an architect and founder of Red House Studio in Cleveland, Ohio.
So we've landed on Mars.
You've landed on Mars. It's pretty inhospitable. I mean, what are you going to do?
You have dust, you have a little bit of gas in the atmosphere, some water, subsurface water that's in most cases, full of perchlorate. So it's not great. It's not drinking water for sure, but it can be filtered. So NASA or any space organization makes this trade-off if they're going to take a shelter to a destination, but it costs you energy and it's really going to slow you down. It's going to cost you a lot. And you can just have enough faith in yourself that you'll build your home when you get to destination.
So this is where Chris and Red House Studio come in. So Chris's vision is to grow mycelium homes in space.
Oh, here we go, Connor. Oh my God, you couldn't wait. You could not wait.
I know,
We've
it's just
gone
like
now from poop to mushrooms yet again. I'm
Poop.
feeling like you're a one-topic wonder.
I'm not. It's space as well, right? I added something. It's poop and mushrooms and we and
Okay,
space.
that's fair. Nice development.
So space is where all the fungi are.
Sounds pretty crowded in there. I can't imagine there'd be much room.
We just done 2 fungus puns line after line. That's pretty unacceptable. But hey, it's our podcast. We can do what we like, right?
Okay, seriously, how does all this work exactly with Martian soil and everything? I mean, we saw Matt Damon do it. Was it real? Was the Matt Damon Martian movie a documentary?
Actually, Matt Damon did it wrong.
The soil there is inorganic. Some of the way we're looking at using this is actually bind that soil, use the mycelia to bind it a little bit like cement does with concrete, so it won't grow on it the same way that it would do biomass. The project that we're talking about actually has to grow an autotrophic organism first. So we're using a cyanobacteria that is a colony forming cyanobacteria. So it's, starts off as this little tiny algae, but then they start to link up and form colonies that are hair-like colonies. So that biomass is what then the fungus would use to grow on. The algae also do the service of fixing nitrogen. So there's a type of organism called a diazotroph, and they are amongst the very few organisms that can actually take nitrogen from the air and then convert that into biomass. It's a little bit like a lichen where the plant and the fungus grow together, but the plant and then the fungus comes on a little bit later, but for all intents and purposes, we're liking the project the way it is.
Oh, this is extraordinary.
It really is. I mean, in many ways, what Chris is describing here is recreation from billions of years ago, the sort of hypothesized great oxygenation event when cyanobacteria and what have you made all of the oxygen that we breathe, and then the fungi evolved, and then it was plants, and then it was dinosaurs, and then here we are, it's podcasts.
So how does Chris control the fungi and make sure that they do what he wants as they create the habitat?
Well, he's planning on growing them in a bag.
And the bag is like pretty much a laboratory in itself, and it's an environment within itself. The membranes have everything from artificial light to artificial heat, air exchange, and so it's a very biomimetic in the sense that it's almost like a living organism in itself. We have all of these cells that we plan to fill with the material, and so first those cells will have the algae within it, and they'll fill with water and carbon dioxide, and then that'll be like kind of a small biome just for that algae to grow. And then once that reaches maturity, there'll be another process that happens that starts to dehydrate that and prepare it for myceliation. So it needs to be like the perfect moisture content for the mycelium to start to grow through that. So it dehydrates a little bit, but it still has that hydration to it that can feed the mycelium.
And during this process, oxygen.
That's a pretty good thing too. We're going to need that. So we can store that oxygen, and that becomes, something that actually could at one point scrub the carbon dioxide that the space travelers produce. But in this case, we're actually going to store the oxygen because the mycelium is going to need that as well. And there needs to be, fresh air exchange in between that happening because the the cyanobacteria is going to turn carbon dioxide into oxygen, and the mycelium is going to do the exact opposite. That'll respire oxygen into CO2.
So these exchange systems kind of work the same way that the human body or multi-celled organisms deal with getting oxygen to the right parts of the body, perhaps through holes that can
Exactly
only
right.
allow water to go through them.
Biomimetics at its best.
So let's say NASA or Elon Musk or Jeff Bezos, all the wealthies who go up to space, they're going to send a spacecraft up to Mars and drop an entire village or a town onto the planet, and then come back months, I guess it takes years, really, realistically speaking, and job done. Your house is ready to go.
And it's not just any old house, right? It's a house of comfort too.
If we plan to go to Mars in the 2030s, if this project's already starting to grow in the late 2020s, then we not only will the buildings be there and you can build many of them, but you have the opportunity to test those with missions that happen in between. First thing you're going to want to do when you get to Mars is go, get a shower, go straight to bed, and, spread out a little bit, because you now have been in a spaceship for about, 6 months, and a little bit of private time is probably necessary for all of the travelers. And we envision actually, not only growing the structures, but growing the furniture using the same process, to have soft materials that are kind of spongy, some materials that are, foam-like, that can be very nice to lay on. And then there is actually ways of making, leathery substitutes, or actually fabric-like materials from the same processes or similar processes that use microorganisms to create the material. So almost everything in the room you're in now could be substituted with this process.
Now let's talk about the radioactive elephant in the room. Radiation.
Right, because we know that outside of the protective magnetosphere of the Earth, there is dangerous ionizing radiation. But get this. Mycelium is kind of magic in that way. It can be used to protect space travelers from that radiation.
Fungi are excellent at coping with radiation. So I think researchers first noticed this when at Chernobyl there were some fungi that were really proliferating around there, and they brought it back to the lab, and they noted that the mycelium actually grows towards the radiation source. So fungi, just like plants take visible sunlight and convert that into biomass and sugars, fungi can do the same thing using ionizing radiation. So that includes things like UV radiation, X-rays, gamma rays.
So look, here's just another example of an organism that's millions of years old that has managed to solve a problem that we've frankly created, and it's just another example of turning waste or a liability on its head and making it a resource.
It sounds like Chris has the best job in the world.
Oh, thanks. We have a lot of fun.
I guess now it's time to come back down to earth and say thank you for listening to Discovery Matters. Our executive producer is Andrea Killen, and this podcast is produced with the help of Bethany Grace Armitt Brewster. Editing, mixing, and music is by Tom Henley and Banda Productions. My name is Dodie Axelson.
And I'm Conor McKechnie. Make sure you rate us on Spotify or whichever platform you use. We'll see you when we come back with another episode of Discovery Matters. If you enjoyed listening to Chris talking about mycelium, there's another episode including Chris coming up in Fungi Part 2. Bonus points to anyone who can spot and name the science fiction series with musical references in this podcast. Great to hear from you all. Nanu Nanu. Can't get enough of space tech? Tune in to the 8th episode of the podcast Water and Future, presented by Aquaporin. They discuss Aquaporin Space Alliance's collaboration with NASA and why it's essential to reuse what you have in space, even astronauts' urine.